Okay, sorry. Okay. So, well, I mean, this is a very old idea in topology, the idea that continuous motion can be simplicity approximated. I'm trying to get you to see in this particular example, dimension 3, that if I'm not worrying about the points, I'm going to start with the curves in the one skeleton and also the surfaces. I need sort of 2 bits of information to record the motion. And as I get finer and finer triangulations or cell decompositions, I have a better and better approximation to the model. Now let's kind of remember that and what the information is, and then discuss the combinatorial model and then see what the algebra says a motion should be, and then fit these 2 things together. Now, I guess it's I don't want to go into this in much detail, but if you look at the actually break down the PDE that really describes the motion of an incompressible fluid and write it kind of as invariantly as you can, besides the metric, it uses some data which is just purely topological. So one is the quadratic form on one forms, and I can which is this. So let A to be a, well actually let A to be a one form, and then we can form this expression. And this will be non-degenerate if you restrict yourself to co-closed one forms and ignore the cohomology. And if you also look at this tertiary form, these 2 pieces of data allow you, with the metric, to write the PDE. And in fact, I can recall when Jim Simons, during one of these summers in the 70s, said, hey, a 3-manifold has this great quadratic form on it that doesn't depend on anything. This should be important. Anyway, and of course, to a topologist, this is very nice. This is just the self-linking number of the generalized curve defined by this exact 2 form. Anyway, to write the fluid equation, you need these 2 things plus the metric, and both of these things, this is like self-linking phenomenon, and this is essentially by Planckery duality. You can think that the wedge product of 2 one forms is determined by all of these scalars as you let this vary. So this is really the ring structure from 1 to 2, which geometrically is just like you have two surfaces with boundary, and you see how they intersect. So this is like the intersection theory, and this is like the linking theory in the 3-manifold. So whatever this this fluid thing is, it's somehow described by the metric plus this topology. So it's worth trying to think about this in a point of view of algebraic topology. Let's see. Well, let me just make one more little remark about this. If I call this thing, so this is, let me have some notation. This quadratic form is given by this, and this is given by this. Then if you define a bracket phi, now if you use the metric to, let's see, if you define a Lie bracket by, if you define a bracket let's A to 1, A to 2, by saying that this this quadratic pairing applied to these two guys, so this is to be defined, should be equal to this. So if you restrict yourself to the space of co-closed forms, this will be non-degenerate, and this will be defined. Then this, so these two things, this symbol and this symbol, then define a Lie bracket, and this turns out to be the, when you identify co-closed one forms with the volume-preserving vector fields, this is the just the Lie product. So this is the Lie algebra structure. So the Lie algebra structure of volume-preserving fields is sort of contained in here, and this is like a bi-invariant non-degenerate form, killing form. And so anyway, this is a nice package of structure. It sort of has the algebraic topology and the Lie algebra of the group of diffeomorphisms all sort of linked together, and the fluid equation is just this data plus the metric. But we can't understand it. There's no theorem that says this equation can be controlled and so on. So, so what we'd like to do is restudy this thing with different models, like you cut off the geometry and make it discrete. And so I'm going to try to think of the vector field as approximated by these simplicial chain things. But if you just use the idea of chains and homology, that won't be rich enough, because you have to have these nonlinear things in there. And as I said before, these things don't have a canonical form. So anyway, this is why I want to try to make this combinatorial model. Okay, now now there's sort of a lot of help you have in trying to make this work, because this structure of forms in D has to fit with the algebraic topology, and so your model, which is going to replace this or supplant it or complement it, has to fit with the topology. And there's lots of ideas around. So I mean, well, so let me just launch into what the model is going to look like. So let's take some cell decomposition of our space, and I'm thinking like of a fine cell decomposition, and the model is going to have the following. Well, let me start a little more slowly. Let me describe something which is something that follows from some work that Quillen did, and it goes like this. So let's just relax the geometry, just kind of forget the geometry and for a second, just think about the homotopy theory, because somehow this information has to be consistent with that. So let's see what we can get. So now this theory works better if the space is simply connected that I'm about to describe. So let me start with the simply connected space, and so it has no, and I'll suppose it has only one vertex and no one cells. So I'm just going to discuss some homotopy theory. So it starts off with, say, some spheres, and then I attach some cells, and then some more cells like this. Now, there's a nice algebraic model of this which follows from a theory of Quillen, and this theory itself is based on a construction first of Kahn, a combinatorial model of the loop space, and then his student Curtis made a simplification in the simply connected case, and then this simplification was used by Quillen to make an algebraic model. And I will now describe a picture of something which is very nice and easy to remember, that follows from all this stuff. And it goes like this. So first of all, if you just, let's just look at the first stage of this. This is a bouquet of spheres. Now it turns out the homotopy groups of that, the graded homotopy groups of that are quite rich. It turns out it's the free Lie algebra generated by one symbol for each sphere. And you put that symbol in dimension one less than the dimension of the sphere. So if these are all two spheres, you put them in degree 1. If some are 3 spheres, you put those in degree 3. So you write down the first spheres, say, and you take just the Lie algebra generated by this. And because these things have a dimension, the commutator is this thing with the sign. It's really a super Lie algebra, you might say. And now this free Lie algebra is the homotopy of this bouquet of spheres. So the attaching map for this cell, say the next layer of cells that you attach, are given by spheres, so they're in this Lie algebra. So then you can attach some new, so you take these cells, call them C1, C prime, and you add those cells as new generators, C prime, C prime prime. And now, and you put them in dimension 1 less than they are, and now each of these has a boundary, which is a sphere. It's in the homotopy groups of the space below, but that's just this Lie algebra. So you can define that a boundary of C is going to be like whatever formula. It could be, bracket, bracket, E prime, E, plus some other expression, and then you do the same thing for C prime, and so on. And then you just you take the free Lie algebra generated by these guys, and then you make a boundary given by the formula for the attaching map. And then the beautiful theorem that comes from this stuff is that this new guy is a Lie algebra with a boundary operator. Oh, you extend the boundary operator to be a derivation, so it's defined on all of L. And then if you take homology, look at the kernel of D mod the image of D, it's a theorem that that's the homotopy of the new space that you get by attaching these cells, at least if you tensor with Q. So let's just think of them. Huh? All of it. All of it. With a shift of 1, yeah. Yeah. It's the graded stuff here. It's really like the homotopy of the loop space of this space. So that's a shift of 1. So then we look at the next cells, D, D prime, and so on. Their boundary maps are given by formulae, which are cycles in this thing. So we can attach new generators, D, D prime, and the boundary of D, D prime, is going to be some formula now. It's going to involve the E's and the C's, and this formula is going to be something whose D, which is already defined before, is 0, because it's a sphere. And these formulas won't be canonical. You'll have to choose a representative formula for the homotopy class, but write them. And D squared will be 0 because D of this side is 0. So you add these new variables, and the theory says this object computes the homotopy of the new space. So then you go on. So here's a sort of actually I should have, here's a algebraic model, a nonlinear algebraic model for a lot more than what you're used to. I mean, it could have been that this could be a real cell complex. So, if you normally would compute the homology, you would have the cells, you would just take the cells in each dimension and take the abelian group they generate, and then you would look at how they attach, and you get, the ordinary boundary. And if you take kernel mod image here, you get the homology of the space, right? So if you look at this formula here, this boundary, actually this boundary will have a first term. See, these guys here, there's sort of a first order part, which are just the sums of E's and C's without any brackets, and D's and so on, plus signs. And then you have the bracket expressions, and then you have the triple bracket expressions. So the way this thing looks is that the real boundary that you get is it breaks up into pieces. It's got a first order term, which is the usual cell boundary. So if you just take homology at this level, so to speak, and ignore the higher order terms, work with this complex modulo brackets, make it abelian. Take the Lie algebra and make it abelian and compute homology. You just get the homology of the space that you started with, shifted down by one. And then there's a quadratic computation you could perform that computes something else. And so on. So this is like an extension of the usual picture that we have, except the first order aspect of it is just the ordinary homology of the space. Okay, so this is something that you sort of know exists. It's, in the simply kinetic case, this would be called the Quillen model of the rational homotopy type. So it's a very nice thing. It's something which is it's a Lie algebra. It's just free as a Lie algebra. It has a differential, and the first order information in it is just the additive homology. So let's see. So let me just Curtis Quillen. Let me start going this way. So Planckery, in like the second analysis thesis paper, switch from defining homology in terms of submanifolds to using triangulations and define the dual cells and so on. And so he defined, in a sense, you might say, the first order term here. And he also, in the case of a manifold, of course, discussed what we call Planckery duality, which has a little bit to do with the ring structure. I guess the general statement was done by Whitney in the 30s that the homology has a well, he didn't say it this way, but he talked about the cohomology has a ring structure. But let's say if you have a manifold, the homology forms a ring. You have the intersection theory. I shouldn't say it that way. I should say the cohomology forms a ring, and the homology forms a coalgebra. The map going in the other direction. And so Planckery duality uses a part of that, but sort of the fuller ring structure is what Whitney discovered. And then, of course, this fits with de Rham and this wedge here. But if you look at a formula for the ring structure on the chain level, it's going to be a map from the, if you look at the co-ring structure, it's going to be an approximation of the diagonal, and the map from the space cross, the diagonal map from the space cross itself. And if you take some kind of Saylor approximations of that, then you get this coalgebra structure, and let's make it symmetric by just flip it over and divide by 2. And it turns out this, so the D that I said has this sort of first order term, which is just what we're used to, is from the cells, the faces. The second order term will just be given by this map here. And I mean, you have some E maybe, and it would go to a term like this. If you think about the with the grading that you're used to, something of degree n goes to ij, where I plus j is n. But if you subtract 1 from each one, then what you have on this side is 1 less than what you have on this side. So it's okay for the boundary map to go down like that. So this will work with this shift. So the second order term in this thing is exactly a choice of the ring structure. And now one knows that you cannot make this choice in general, in sort of a local way, so that I've made the choice to be commutative, but you cannot make it to also be associative in general. So there's going to be, if you write down the associator, it'll be, or the co-associator, if you look at the map this way, it's going to be null homotopic, and there'll be a chain homotopy that corrects the fact that it's not associative on the nose. And now you're going to have a map from one thing to three things, but it's a chain homotopy, so it adds 1, but you're subtracting 3 times from here and adding 1 and subtracting 1 from here, so the difference is still 1. So that's the next term of this thing. So it's the sort of some homotopy you choose to correct the fact that the thing is not associative. So you might say that you kind of start from, in this structure here, I mean, actually when I was a graduate student, we sort of learned this first before we learned about this. I mean, about forms. We sort of learned about this cell approximation first. And this was the famous thing of a Steenrod, that if you actually don't work with rational coefficients, but you actually work over z, and you're not allowed to do this symmetry, but you start looking at the various chain homotopies that you have, then you build these famous Steenrod cohomology operations. Then you might think of what I'm saying now as some kind of Steenrod structure O over Q. You keep looking at the diagonal approximations, but in the fact that they're all chain homotopic. And this idea is actually in thesis of Stashev in a slightly different context. The idea that you can talk about an algebraic structure which is sort of associative, and you can correct it, and then that has the correction has some structure that has to be corrected, and so on. And this forms a fairly combinatorially complicated thing. But anyway, the claim is that this can be organized as a nice thing. It's just a picture of the differential in the Quillen model of the rational homotopy theory. And so you see there's kind of a duality here. Well, so we have to, there's some kind of a duality here, because there's a famous thing in topology called the Ekman-Hilton duality. It's sort of a duality between homotopy and homology. Actually, in fact, I should start this first as a name before this. Van Kampen. Van Kampen. Now I want to. Okay, so now I want to go back to the. Let's just sort of kind of stop in the middle. We have to come back and discuss this some more. But now I want to go back. Suppose I just have a general cell decomposition of any space, and these. Now I want to think more geometrically. These might be small cells. I might be trying to approximate this fluid problem or some other problem. And now there's a certain amount of fearfulness going on now about the 0 skeleton and the 1 skeleton. And I've learned to not be afraid of this from Maxime, who's not afraid of it. It's just algebra. You just do it. So Maxime Kontsevich. But anyway, I'm still a little bit afraid, so I'm going to suppress the zero skeleton for this talk. So you can always do that by choosing a maximal tree in your cell decomposition. So you think of the tree as being one base point, and then you make a model like this where, so now I'm going to say again what the model is. Before I was saying what it was like in the homotopy category and how it fit with cells and what it means and so on. Anyway, so the model like this. Now this is, these mean, you put these in degree 0. These are the one cells outside the tree. So these, so to speak, give you free generators for pi 1 of the one skeleton. And you take the free Lie algebra they generate, and here you put in degree 1, you put all the 2 cells. And in degree 2, you put all the 3 cells. So in my case, we would be done. And then the claim is that in this model, in this free Lie algebra, there is a differential which has this form. It goes on forever, going deeper and deeper into the bracket structure. It satisfies d squared is equal to 0. And I sort of now don't say what it means. I just say it exists. But it's a certain, it's just there. And the differential, though, is constructed out of these same ideas. You look at the first order term will be just the boundary map. The second order term will be the cochain cut product. The third order term will be the correction term of the failure of associativity, and so on. So this will exist because the Steenrod structure, it's a local construction, and it doesn't care whether the space is globally simply connected or not. So, and you can sort of think of the first 2 stages here as being analogous to what we know of as the Van Kampen theorem, that says that you can make a presentation of the fundamental group by taking one generator for each one cell and one relation for each 2 cell. But I'm not giving you a group here, I'm giving you a Lie algebra. Groups and Lie algebras are not the same. And there's an interesting philosophical point here because, you see, and then Kahn basically made some kind of a free group thing with some kind of boundary stuff. He made a free group thing with some boundary stuff which generalizes Van Kampen and which gives you an actual combinatorial picture of the loop space of any space. So the components give you the pi 1, but it actually gives you the full loop space. Now, the reason I draw a line here, though, is that, as we know, problems in group theory are not decidable. They're not algorithmically decidable. So you can't, even though this is a combinatorial description of all the information, it's not, you can't extract anything you want. So in fact, you should actually kind of forget now about the problem of having a model that gives you the pi 1, because that's not decidable. You want to have something, you want to use this Simon's rule to calculate. You want to be able to calculate. So what you do is you just, so to speak, make this free thing nilpotent. Well, this is one thing you do. So I want to just, this is the thing I'm doing today. You pass to a calculable thing by making it sort of free nilpotent to arbitrarily high order, and then you can pass to the Lie algebra if you have Q in your coefficients. And then this thing exists, which is some kind of softening of the full undecidable thing here. And the softening was done by Curtis in '63, Ed Curtis, but this still was a semi-simplicial world, and then Quillen's famous paper puts this in a differential graded world, and this is what it does. But then, because of this pi 1 business of not being decidable, the formal theorem here is about simply connected spaces. But the idea is that you can use this algebra anyway as a model, and you can use it when the cells are small, and somehow you're approximating the continuum stuff. But it is a cutoff. So you have killed the high frequencies and the Sobolev spaces and stuff, and can hope to work with this itself. So let's see. This goes to 11:30. Okay. Well, there's this thing of duality. So here we have this thing which is something like a group. It's actually the Lie algebra of a group, you might say. It computes the homotopy of the space when you can make the grand computation, shift it down by one, as a Lie algebra, in fact. That's the Whitehead structure. But the first order term of it computes the homology of the space. And the second order term computes the cut product. And then the third order term, it computes something which is a little bit subtle to describe. It's new. I mean, we don't have a word for it. Anyway, you have this natural nonlinear thing which you could truncate at any height you want. So you can set all the brackets below some point to 0, and then you have a finite computation. And it has the same form algebraically as the thing you start with. So this is what I say, a combinatorial model for nonlinearity. This thing can be truncated, and it has the same form. The bracket, it's the map from the full thing to the truncation is a homomorphism of all the structure. So we haven't lost any of the form of the computation. And now there's a dual description. That's actually the one that I worked on in the early 70s. It's a differential graded algebra. It also has lots of variables and so on. And then you have a d squared is equal to 0, and you take the free commutative algebra generated by that. So this is something you can pull directly out of a de Rham complex by so-called finding a free algebra that maps in, giving an isomorphism cohomology. And now again, this D is a sum of things. Now this globally computes the cohomology, but the first order term computes the homotopy. And then the second order term computes the ring structure on the homotopy, and so on. So this is part of this dual picture. I mean, in one package you have both the, the thing starts on one side. You have this pi lower star h over. One model starts with one thing, and it builds a nonlinear structure to the other. The other starts on this side and builds a nonlinear structure to the other. And this duality between commutative DGAs and Lie algebras, which I learned from Kontsevich, although it's, as he says, it's obvious and old and stuff, well known, but somehow the essential clarity of this duality was not ever perceived by me. In fact, I've even read papers in homotopy theory about how this duality breaks down by the strongest people in the field, because if you don't express it the right way, it does break down. But at this level of presentation of the object with all of its structure, there's a perfect duality. Anyway, this is and so you can understand the higher terms in a dual way, and there's constructions that take you from one side to the other, called bar constructions, and so on. So actually, you could be on any one side and go back to the other side. But in some sense, for this particular problem that I'm thinking of, where you're studying a manifold with a cell decomposition, this is the best side to be on, because the generators correspond to the cells. Over here, the generators correspond to what's called the Postnikov decomposition. So that's very good if you're studying classifying spaces or things into which you map. But the things you map, the domain, let's say, I think are, so to speak, best described by this side of the duality. Anyway, so the idea is that just take the free Lie algebra generated by the cells, and then you can make a boundary operator that, in some sense, encodes all of the intersection theory. It's like you try to set up an intersection theory at the chain level. You've got to do something to form the intersection. You have to make them transverse. There'll be a choice involved. If you do three things, it won't be associative, but there is an equivalence between the two choices. And anyway, all that stuff will organize itself into this one nice thing here. This a differential in this Lie algebra. Okay, so now this is like an algebraic model or a combinatorial model of the actual space, pieces of space and how they fit together, expressed in a sort of computable way. Now I must say, one more sort of philosophical point, you also, I mean, this is a conference about connections, and well, no, it's not a conference about connections. It's a conference about geometry, but I don't know what the conference is about. Anyway, it's a conference in which connections are prominent, but so this model, as I'm describing it today, is going to be okay to discuss, let's say, this fluid thing. I don't need any more, but if you want to do gauge theory, discuss gauge theory in this model, and you want to discuss flat connections, then you want to put in, so to speak, twist this thing with some lattice gauge field. And this is, I know how to do this on this side, but I haven't understood yet how to do it on this side the best way. So, but since they're dual, I'm not worried. You can do it. So, and so in some sense, you see, gauge theory or mappings of the fundamental group into a Lie group, that's decidable, because the set of representations of a finally represented group into a Lie group is given by a bunch of equations, so it's a decidable thing. So you can sort of think that, one reason gauge theory maybe is so, just from a logical point of view, one reason it's so important is because it is something which is computable. So I would hope finally to eventually have this model souped up enough so that it sort of incorporates, at least from the right point of view, gauge theory as well. And it could very well be that for practical purposes, that's what you can compute. Like maps into certain kinds of groups. You can't really compute the whole pi 1, and so you have to. So I would like to back this up a little bit and put the possibility of putting in gauge theory. But I don't know how to say it nicely here. I can say it there, but that's not so geometric, so I won't say anything. Now let's go back to the problem of the fluid. So now this is a model of the space. It's not a model of the vector field. The vector field is like an infinitesimal automorphism of the space. So we know what that should be, though. We should now take the derivations of this thing, the derivations of positive degree, or you can also have degree 0 if they commute with d. But anyway, I won't discuss that now. So you consider derivations that go up, and so they're just defined by formulas on the generators, and then you extend them by the derivation rule. So you just give a formula for each generator for what the derivation does. So that's so you can see so a derivation that goes up in degree, like say +1, I have to say what it is here on the generators. I have to say what it is here on the generators, and I have to say what it is here. Well, in my discussion before, I was sort of showing you how you do it on the cycles of degree 1, and then on the two cells. So you would sort of take this picture and reinterpret it in terms of the model. And since the model is sort of written out in terms of the cell decomposition, you could, so to speak, write that. And so we can sort of encode in the model as a, say, a +1 derivation, this motion. And now, so this is again, this thing here is also a Lie algebra. If you compose two derivations, form the commutator of two derivations, it's also one. And it has a differential, which is the commutator with the d that I have here. So this itself is another differential graded Lie algebra, and it's supposed to be a model for the diffeomorphisms, or the Lie algebra of that. And so now we can express the approximations to the motion as a derivation here, so we're sort of in here. So now what is the fluid equation in here? Well, there's this beautiful remark of Arnold back in the continuum model where you use these two things. But by the way, Maxime also pointed out to me, these are, of course, the two terms that occur in the Chern-Simons invariant. If you write ADA plus 2/3 A cubed, this is a matrix. You expand out all the terms. Everyone can be written out either in this form or this form. Right. So, sort of also related to that. Not sure how, but at least formally, this structure allows you to write this. See, what am I saying now? Oh yeah, so there's a remark of Arnold that the incompressible fluid flow without friction can be thought of as just the following thing. You take this Lie algebra that I defined here, and you take the L2 norm as a function on the Lie algebra, and then you also, by duality, you can think of this, call this thing G, but G star be the dual. So you also have a norm here on the dual. And the dual, well, the points here are, well, let's see, the functions here, let's say the functions on the dual contain the linear functions. They're the same as the points of G. So they have a bracket. You extend that bracket on linear functions on G star to the polynomial functions on G star by the derivation rule. This gives you then a Poisson structure here. And if you have a function, then you can define the Hamiltonian flow. And Arnold's remark is that for that construction, this Lie algebra with the L2 norm, that Hamiltonian flow is the Euler flow, the flow of the fluid. So this is like, and then he and his students have discussed lots of different kind of Lie algebras where you can look at that and you get lots of other nice examples of PDEs out of this construction. But anyway, that's on the continuum side. But now we have a nice Lie algebra. We have lots of Lie algebras. In fact, we can truncate this. We have all these Lie algebras for one triangulation. And in fact, if you subdivide, it turns out, you know how this happens. It turns out when you subdivide, you actually have to add a pair of generators and set one equal to 0, and the boundary of the other one is that. It turns out that when you subdivide, the new Lie algebra is isomorphic to the old one with just this term here. But I mean, the isomorphism is very non-trivial, but it exists. Anyway, you understand, in a sense, how all these look as you subdivide, and so you have a whole vast array of Lie algebras. You can truncate them to any order. Now you have finite dimensional ones. You can take a metric on your space and induce one on these cells, and then induce one on any of the truncations. And you have the Lie algebra structure, and then you apply the Arnold remark to construct the flow, which, if all this were converging to the stuff over here, would converge to the Euler flow. So that's a whole system of finite dimensional models, sort of Hamiltonian models that hopefully, I mean, this is like work in progress. I can't even make a statement, much less state a theorem. But anyway, this is kind of a program. Anyway, this seems to be a natural way to get nonlinear cut-off models that converge to these sort of things that are considered to be very hard. So, thank you. That's the end. All I have to say.
What do you expect to look for in the model that will clue you into the preservation of dissipation singularity state in the fluid flow?
No idea. No idea. That's like, I mean, right now I don't. I set myself a different kind of question, which is, that would be nice to answer that one, but.
Wasn't that similar to what you said at the beginning? That was one of the things we're looking for.
Oh no, that's a motivating problem in the field. But I would actually, the answer could be this way or that. Fluids are still there, and we want to have models for them in any case. So I was really concerned with the problem. I want to make a model that you can go home with, or put it on a go talk to Folkert and he can do a computation. You could put it on something and compute, and maybe you could prove something in the limit about this. I actually think that if you could prove a theorem, it would be something more like there would be some sort of non-obvious completion of this discussion on which the Euler flow is defined uniquely for all time. I would be very happy to prove that. And whether or not the smooth things inside of it stay invariant for all time is another question. But that question would become less important, because if you had a way a thing to compute with, you go around it. It would affect the estimates of the computation. If you looked at it with certain norms, it would affect the estimates of the computation. But it could be that there are other norms. I would like to understand that, obviously, but it's like you don't have to understand that to still have something you can work with. It's like you don't have to stick to the same problems that you get from your grandfathers, so on. Yeah.
If you give us one of these differential graded Lie algebras, do you know how we can tell if it's a manifold?
Yes, the right person, actually. But I just had Andrew Renitzky here for last week. He has the latest word on this for higher dimensions. But that's another thing. There is an algebraic, in some sense you have to add, to complete the picture. In fact, I was a little kind of vague at the end here about volume preserving and stuff. Besides being overall vague, there actually are some. What?
What question are you answering?
Yeah, so the question is, I've discussed this as a model of the algebraic topology only, and the question was asked, how do you see the manifold structure itself in there? And one aspect of it, this is like let me draw a line here. There are two parts. So there's the understanding that we have in dimension greater than 4, and that is basically that you have to add a kind of local Planckery duality. So this, you could say, globally has to satisfy Planckery duality, and then you add in, there's a beautiful stuff of Renitzky about talking about a complex being localized over a thing like this. Or actually, he described it over a space, but since this is a model of the space, we can imagine doing it over a thing like this. So the chains have to, when you localize them over the space, have to satisfy Planckery duality locally. And he has a theorem, it's a fantastic theorem. I just learned this week, actually, because when I left this field 30 years ago, there was a definite gap in what was understood, but now it's understood completely. and because of his work. And the chain expression of Planckery duality locally carries the information. Now, and then you can talk about any coefficients and so on and so on. And if you really want to get an honest theorem about a manifold in the usual sense, you have to sort of work over Z. And I've got to go back and add some other stuff to this, because this is a model over Q. But anyway, it's, you know, and that's not so easy either, because you have to do integral homotopy theory. But I mean, you know how to do it with this stuff here. But so that's above dimension 4. Now, when you look at things like the Donaldson invariants in dimension 4, they're also combinatorial. They don't require the smooth structure. They're just combinatorial invariants. And now the Donaldson invariants require you to know more about the space than it satisfies local Planckery duality at the chain level. What you have to know is that the local links and so on have no flat connections. If you can, like with values in SU2, if the local links look like homology spheres and they also have no flat connections, then this thing looks like a 4-manifold as far as the Donaldson theory is defined. And you can compute the invariants. Let's say you can define them and show they exist. So in fact, if I can do this step here, putting in gauge theory, then I can also localize this and then do the gauge theory also a local way. You can formulate, at least correctly, a conjectural picture of a 4-dimensional space. But anyway, so that, but it would use everything, you know. It would, you know, there's a lot of steps I don't. Okay, yeah, that was it. Okay, thanks.